We continue now in the time value of money. We've finished introducing the time value of money. We spent a little bit of time making the case that you can't evaluate pizza by linear inch, nor can you evaluate investments by just summing up cash flows over time. There has to be some kind of a transformation of those numbers so that we have equivalent amounts. Talked about the time value of money. We spent some time on the future value of a single sum of money and worked out in different ways and finished with showing how much the importance of compound interest. In this lecture now, we're going to talk about discounting. Remember, compounding was going on the timeline from left to right. Now we're going to talk about bringing money back to the present, going from the right to left or from the future to the present. And we're going to present another formula for the present value of a single sum of money, and then we'll go over problems to look at those. The reading assignment, we're still in Chapter 9. I've made this statement before, I'll repeat it, that of the chapters in the textbook, this is the one that follows most closely with what we're doing, and it forms the basis for investments, and it's worth spending some time and reading it. Looking at present value of a single sum of money, we're discounting. And we talk about discounting, we're converting future dollars, some money that we will receive in the future, we're converting that to an equivalent amount today. When we were compounding, we were taking a present sum of money and we were converting it to some future period. Now we're taking that future sum of money and bringing it back to the present. First, we'll start with the formula that we've already presented, the future value of a single sum of money. We'll do some arithmetic by dividing it by the 1 plus r to the nth power, which is 1 plus the interest rate raised to the number of periods. If we do that, we have the future value divided by this factor of 1 plus r to the nth. And for convenience in presentation, if you remember, if you have some denominator 2 raised to an exponent, you can basically move it to the numerator by changing the sign of the exponent, which we do. So these two equations are equivalent by using our rules of exponents. And the only reason to do that is just so that equation is on the same line. Also, I think it's useful because if you look at the two equations, they look very similar, but we're changing the subscripts. And notice that when we are compounding from the present to the future, the exponent is positive. And when we're discounting, since we can think of that bringing it back from the future to the present, the exponent is negative. So, if you associate that in your mind, then these two equations are, as you look at them, are easier to remember. Okay, the general formula, we're taking some future sum of money, this V with the subscript with the capital N. We're multiplying that by 1 plus the interest rate minus, and notice that we have the big N minus the little n, where n on the timeline is some future period of time relative to the little n. And again, this equation can be simplified in the way we present it. If we assume that n, the little n, is equal to 0, representing that this is the present period, if we do that, we're basically saying, let's take some future sum of money, represented by the V with the capital N, and we're going to multiply that by 1 plus the interest rate minus the number of periods that's in that time period, or it's in that time frame. Okay, looking at it from the problem, starting with problem 4A, what is the future value in 10 years of $10 today if it draws interest at 10% compounded annually for 10 years? Cross-referencing this now to our timeline, you see that at time 0, we're putting $10 into the bank. We want to know in 10 years how much will be in that bank that we represent as that V representing value, subscript 10 representing the end of the 10th year, and the interest rate is 10%. Since there's several things to look at now, and I know this is somewhat tedious, but as you get into more complex problems, if you follow this logic, it's going to be a lot easier. The logic is, first of all, recognize that we're dealing with single sums of money. So we know we're going to use a single sum factor. Also notice that you're going from left to right, meaning that you're trying to convert that sum of money to some future amount, which means we're going to use the future value then of the single sum of money. And so we use the future value of a single sum of money formula. The present amount is $10. The interest rate was given at 10%. The number of periods is 10. We plug that into our calculator at 10N, 10% I. We have the present value is a negative $10. The payment is 0. We calculate the future value, and it comes out to $25.94. Okay, for problem 4B, and I'm relating A and B, now let's ask the question, what is the present value of $25.94 received 10 years from now if the interest rate is compounded as 10%? But now let's work it out so we can see that our equations work. In this particular case, notice that at the end of the 10th period, we have $25.94. The question is what is that worth today? Okay, where today is represented by time period 0, given that there's the interest rate at 10%. So the question is which equation do we use? Again, through logic, we see that we're dealing with single sums of money. So we know we're using a single sum of money formula. But in this particular case, because we know the future amount, which is $25.94, and we're trying to solve for the present amount, we're going from right to left on the timeline. We're discounting. Given that's the case, then we're going to use the present value of a single sum of money formula. So you see the contrast between compounding, which was problem A, to discounting, which is problem B. Hopefully you can see in contrast why you would use one formula versus the other. The future value is $25.94. The interest rate was 10%. We're discounting back for 10 periods. We pull out our calculator. Looking at this problem, we put 10N, 10% I, zero out your payment. $25.94 is our future value. You key that into your calculators. If you have your calculators, I suggest you again do this. And as expected, as some of you could intuitively see before we punched any numbers to the calculator, that the answer was 10. Okay, now is a digression for just a minute. This is just a digression before we get back to the problem 4A and B. Just so that you can see again that you can calculate the present value of a single sum of money using Excel. And the formula is this equal the present value times these arguments. This rate, which was 10%, is the interest rate that's given. The number of periods was 10. The payment in this case is 0. We'll get into annuities soon, but not today, so we're still zeroing out the payments. The future value was given at $25.94. And notice in this case, I didn't put the type because the default, if you have 0 as omitted, then it reflects the payments at the end of period. And in this class, we're going to use end of period flows, so I just lopped off the 0. Okay, there's no 0 on that, but it gives you the correct answer. Again, it's not required, but I suggest as you're going through this, you just as well learn these formulas in Excel. Even if you don't think you'll be using them for a while, at some point, if you know that how to use these, they might become useful for you. Okay, now back to problem 4A and 4B. I did problems 4A and B also to illustrate the concept of equivalence. The statement is that we're indifferent between $10 today and $25.94 in 10 years from today. That's assuming that the interest rate is 10% and we hold everything constant and we make assumptions there's no risk and that you can borrow at 10% or you can save at 10%, so that we're just focusing on the time value of money. If that's the case, you can see that on this first equation that if we have $10, we can put it in the bank at 10% for 10 years and get $25.94. On the other hand, if we had $25.94 in 10 years and we wanted $10, then we could borrow the $10 today. You can swap back and forth through time seamless, so you'd be indifferent. If you had $10 today and you wanted the money 10 years from now, you'd put it in the bank. If you had a promise at $25.94 10 years from now and you wanted the $10 today, you could borrow $10 at 10% and then you could pay off your debt at the end of 10 years with that endowment of $25.94. Either way, you're indifferent. That's what we're doing with the time value of money, is we're converting money from one period to another that makes us indifferent. That allows us then to compare money through time. Okay, now this particular chart is not quite as easy to understand as the chart that we used in compounding, but the principle is the same. What we're asking is what is the present value of some dollar that you're going to get in a future period of time? What is it worth today? Now, obviously, a dollar today, if we're looking at time period 0, a dollar today is worth $1, right? But you've already told me that you wouldn't agree to lend me $100 today if I'm only going to give you $100, 1 year from now. Notice that its value goes down. Notice that $1 40 years from now, in today's dollars, is only worth about a dime, because there's 40 years that you don't have access or use of that dollar. You'd only give me a dime today for the promise of $1 40 years from now. And at 6% interest rate, that dime over 40 years would grow into $1. So you have that same concept of indifference. Okay, what is the present value of $2,000 that is to be received 5 years from today, and interest rates are 10% compounded annually? Okay, that's a lot of verbiage and a lot of wording. That's why we go to the timeline. The timelines are useful in picking out the information of the verbiage that contained in the problem. And what we're saying is, looking at it, if in 5 years we receive $2,000 and if interest rates are at 10%, the question is what is that worth today? Or what would you give me today if you could earn 10% on your money if I promised to give you $2,000 5 years from now? Think of it that way if you'd like. Isn't that what investment's about? If you're going to pay me money, you're investing in something, you want to know what you're going to be compensated. And if we agree that you're going to get 10% on your money, how much in your investment should you pay me today so if you get $2,000 5 years from now? Is that what investments is about? You get an offer, somebody's offering you an investment, how much should you pay for it? Well, it depends on, well, what kind of return do I want? Or what kind of return does the market bear at this particular time? We see in this particular case, again, that we have single sums of money. Also notice that we know the future value and we want the present value, so we're going from right to left, from the future to the present. So we're going to discount, so we're going to use the present value of a single sum of money. Again, it's important that you go through that logic now so that when we get into more complex problems, it's second nature. It's going to save you a lot of time if you get engaged now in these simple problems. Okay, the future amount is $2,000. The rate is 10%. We have 5 periods. So we put that in our calculator as 5N, 10% I. We zero out the payment again to make sure the memory fields are cleared. The future value is $2,000. We solve the problem, and it comes out to $1,242. So when I started the time value of money problems, you all agreed that you wouldn't lend me $100 if I promised to give you $100 back at the end of the semester. Now we've gone the extra analysis to show you that how you would determine, how much you would lend to me. In this particular case, if I said I'll give you $2,000 at the end of 5 years, and you wanted to earn 10% on your money, no risk, then you would be willing to pay $1,242, or you would lend that to me and I would give $2,000 back to you in 5 years. You'd get 10% on your money and we'd both be happy.